Okay, welcome back. As I said last time, we're going to pick up here next time. I had asked you to answer these questions on your own. What are waves? Well, the whole reason why we're talking about this is because of energy. If it didn't have something to do with energy, it probably wouldn't be very useful to people. So, that's one of the key things here. A wave is a disturbance that transfers energy through matter or space. And space is a vacuum. There's no particles. So there's matter and not matter. And when there's no matter, it's called a vacuum. What happens to the matter that a wave travels through? Well, the wave transfers energy, but not the matter in the medium. Remember, we had two examples of the red particle going up and down, but it didn't actually move along with the wave. And the other one in the compression wave, the particle was moving back and forth parallel to the direction of the wave, but it didn't actually move along. And we said like a sound wave is a compressional wave. And when you're listening to music or the television or somebody speak, you don't feel the wind of the sound wave go by you. Okay? All waves are caused by something that vibrates. Even electromagnetic waves that travel through space are caused by the vibration of electrons and magnetic fields. Mechanical waves, mechanical energy, okay, they have a mechanical wave requires a medium through which the energy to travel. Not all waves are mechanical. So remember, mechanical energy is the energy of a system, and the system would be like the air as the wave travels through it. It would be all the particles moving together. Okay, and on this last part, it says use the table to compare and contrast longitudinal, which are compressional waves, and transverse waves. Well, the matter in the medium moves perpendicular to the direction of the wave. And of course, here the matter in the medium moves parallel to the direction of the wave. What's common to both of them is the matter is not transported along with the wave energy. Transverse waves have crests and troughs. Longitudinal waves have rarefactions and compressions. Crests correspond to compressions and troughs to rarefactions. So we're going to find out that while they both have two parts, the two parts correspond to each other as the wave energy moves through the matter. Okay, now, not all waves are the same. So they have properties to describe the waves, and things like how fast they move, how big they are, how much energy they carry, those kind of things. So the first property we're going to talk about is amplitude. And amplitude is the measure of the energy in a wave. So like in a car stereo or whatever, if you're listening to music, people say that they have an amp. Well, an amp adds amplitude to sound waves. So that's exactly what it does, is adds energy to the sound so it's louder. So when it hits your ear, there's more energy that gets transferred to your ear because the sound wave had more amplitude or energy. So you can think of an amplitude as the measure of energy in a wave. And this also makes sense like with this transverse wave. If you're at the beach and there's a little ripple coming, it's a low wave, it doesn't have much energy. But if you look out and it's a 15-foot wave, you know that it's carrying a lot of energy towards you. The more energy the wave has, the larger its amplitude. Transverse wave and amplitude. The height of the wave is the amplitude of the wave. So it's the distance from a crest or a trough to that normal position, that dotted line through the center, where we said it would be like a pool with the water undisturbed. So it's where the water would be on the tile before somebody jumps in. And then when they jump in, some of the water is going to be up and some of the water is going to be down. But if it was perfectly smooth, it would be at this normal. So the distance the wave goes up to a crest is an amplitude. And the distance it goes down to a trough is an amplitude. So it's this distance from the normal up to a crest or a trough. There's a little clip that we're going to watch. Bill Nye does a diagram of wave length and frequency.
If waves all look alike, how can we tell them apart? Well, please. Consider the following. If
Okay, now he's going to go over some of the wave properties, wavelength and frequency.
waves are nice and even like these, we can't really tell them apart unless we stand in one place. This is our observer kid on a stick. And where she is, she can see the top of one wave. Then as the waves go by, she can see the top of the next wave. Now the distance from here to here, the length, is called the wavelength. That's what we call it, the wavelength. Now there's another thing about waves that you can observe, and it's called the frequency. If you go to the library often, we say you frequent the library. That's how often you go there. So waves like this are coming by often, and we say they have a high frequency. If I slow it down, the waves coming by have a low frequency. Now you know about high and low frequency waves because you know about high and low frequency sounds. Take a look at this. This is an oscilloscope. It lets us see waves. So watch. If I make a high frequency sound,
1,000 hertz at reference fluxivity of 250 nanoweavers per meter.
you can see that the waves are close together and the wavelength is short.
Equalization per NAB standard.
But if I make a low frequency sound,
Full track recording with no compensation for multi-track reproduction.
the waves are farther apart. They have a longer wavelength, and we say they have a lower frequency. So high frequency waves have the waves close together. Ah! And low frequency waves have the waves far apart. See? Thank you for joining me on Consider the following.
There's a second little clip where Bill Nye does a video on amplitude.
When we have a wave like this one, we can measure its frequency by counting the peaks. We can measure its wavelength by measuring the distance from here to here. But there's one more thing we can measure. That's the amplitude. You've probably heard the word amplifier. An amplifier has a volume knob that controls the amplitude.
So the amplitude is the measure of the energy in a wave. So when we add more energy to a sound wave, it makes it louder. So the amplifier is called, an amplifier because it adds more sound energy to waves.
How big the sound waves are. So we can count peaks to get the frequency. We can measure this distance to get the wavelength, or we can measure this distance to get the amplitude.
The amplitude of a compressional wave or a longitudinal wave. This is a little bit different because, we don't really think about these, or they're not as familiar as transverse waves. So the compressional wave, the amplitude depends on how tight and how spread out the compressions and rarefactions are, or how dense they are. The more dense or squished together the compressions and the less dense the rarefactions, the more amplitude. Okay, so the less dense the compression and closer together the rarefactions, the less amplitude. So it's like, in simple terms, it's the difference between the two. The bigger the difference, the more squished together the compression and the looser the rarefaction, the more amplitude the compression wave has. And here's like a picture I made of the difference. And so the top one, like, you can see that this is a compression, and in the place where particles are loose is a rarefaction. But this would be low amplitude because there's the compressions are not very tight compared to the rarefactions. I mean, you can see that the compressions are closer than the rarefactions, but there's not a huge difference. Down at the bottom where the compressions are really squeezed together and the rarefactions are spread out a lot, this would be an example of a high amplitude sound wave. So when those compressions hit your ear, they transfer more energy to your ear, so that's why the sound is louder. And then there's an example of Bill Nye is going to show us about a longitudinal wave. Bill's going to give us a demonstration of a longitudinal wave or a compressional wave.
waves don't always move like this. Now, sometimes they move like this. They squeeze together and spread apart. That's how waves go through something like the spring. Watch. I'll squeeze this end and let go. See, there's a wave going through the spring just by squeezing and spreading. There's no motion up and down. It's the same way sound waves travel through the air. Air molecules bump into each other, so some places they're close together, and other places they're spread far apart. The air molecules are moving kind of like these pool balls.
Midnight Soda Bill needs this shot. Oh! 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 Oh!
It's kind of like that. Kind of like the pool balls, not exactly. As I was saying, sound waves can travel through the air the same way waves can travel through billiard balls. Here we go. Here we go.
Midnight Soda tries it again. He's got it!
It worked. That's because the billiard balls were close together. Now, the molecules in air, well, they're very close together, so sound travels great.
Notice how the energy transfers from one ball to the other. The balls don't actually move along with the energy. Now, it's, the other example that we use are springs. So here at the top one, it shows a high amplitude wave. And there's a big difference between these compressions of the coils of the spring and the rarefactions. So, and springs do move in compression waves because these compressions travel through the medium of the spring. And a low amplitude on a spring, you can see that the compressions are tighter together than the rarefactions. But up here, I said it's the difference between the two. So there's not a big difference between the two. So this would be low amplitude. Okay. And I made a video that shows exactly that. So we're going to take a look at the demonstration of the different amplitude of a longitudinal or compressional wave. Okay, this is a short clip I made to try and demonstrate the amplitude of a compressional wave. Now notice when the spring is pulled back, there's definitely some differences between where the compression is down here and where the rarefaction is. Now there's not a big difference between the compression and the rarefaction. So as we said in the notes, this should have smaller amplitude. Now notice in this case, the compression is very tight and the rarefactions are loose. So there's a big difference between the compression and the rarefaction. So we said amplitude of a compression wave depends on the difference between the two. So in this case, these are very tight compressions and loose rarefactions. And as you can see, there was a lot more amplitude. Now, in this case, I grabbed the spring from about the same position. There's definitely a compression and rarefaction, but the difference isn't as great. So we would expect that it would not have as much amplitude. Now in this last example, I am going to make a very tight compression and there'll be a big difference between the rarefactions. So this one should have the most amplitude. Okay, and as you can see, the compression is very tight, and because I grabbed so much of the spring, the rarefaction is very loose compared to this compression. And it had so much energy, so much amplitude, that it went to the other end and it bounced back, and you can see that the spring had a lot of power. Okay, we're going to stop here and pick up next time. Hope you're having a great day, and we'll see you soon.